Hi Swift Rockies, this is Francis Chari, and I'm here to talk to you today about Xcode Compilation Cache. You might notice that I'm not in the venue, I'm not with you all right now, and that's because there was a little snafu on day one for recording my slides and my talk, so I figured I would come out to the Calgary Zoo and do it again with the animals, and we'll see if we can get this done. So I'm going to talk to you today about the compilation cache, which is a newish feature in Xcode. Xcode 26. We're going to talk about why it exists, the problems it has, how it works, how to turn it on, and how it can help you get the most out of your builds in Xcode, both locally and remotely. So let's get started. So there's something about this comic that really gets me as an iOS developer. I'm sure it does the same for many of you. You look at these people, you think about what you can do while you're waiting for your code to compile. You could get a cup of coffee. You could read a news article. Maybe you could run an errand. There's an hour-long strategy session. Maybe you could compile during that. So we spend a lot of time waiting for our code to be finished building. What do we do while we're doing that? And we spend a lot of effort in trying to improve that, trying to make that shorter. We might split our code up into frameworks and packages. We use previews liberally when writing UI code. Maybe we even do hot code reloading with injection. We might get a Mac Mini, stick it in a drawer and build on that. Or we switch to a completely different build system. Maybe we switch to Bazel. The more we do stuff like that, the more we break our code apart and stray away from Apple's path, kind of the more problems we have though. Imagine you're working on a feature and some code changes and some submodules change and you didn't know that was happening. So you go ahead, finish your feature, push your code up, get it merged, and then it turns out, oh, something subtle broke. But it worked on my machine. So there's this trade-off between speed and correctness, but we don't want there to be a trade-off. We want both things. So before we get into the actual compilation cache, I want to kind of dive into a build itself and have a look at what that looks like. So, a build is roughly divided up into these sections. That's how I kind of look at it. You've got non-code resources, images, strings, storyboards, nib files. They all have to be processed and gotten ready to go. You've got the compile section, which is where we convert Swift code step by step using various parts of the compiler, the Swift compiler, down to object files. These object files are in a format called Mach-O, and they have inside them binary code that can be run on the Apple platforms that we have. Those binary files, those O files, or object files, are then linked into an executable file, and that executable file is the one that can actually be run on the platforms. The executable then has to be bundled up into what we recognize as a .app file, and that .app file is what we can distribute out to various people. Of course, if we want to use Apple's distribution channels, we have to sign that app file so that we can prove what's in it and who we are as well. For our purposes, we're more interested in what takes the most time. And what takes the most time is the compiling. So that's what we're going to dive into now. For the Swift compiler, I sort of think of it in a couple of phases. The Swift driver basically is the coordinating tool invoked when you start a build. It has to basically look through all of your code and look at all of the arguments you've sent in, and then it creates a graph. It's called a directed acyclic graph. And you can see in this small example here, I've got an app that is built with 3 Swift files, and these arrows represent dependency relationships. So the app cannot be built until all 3 Swift files have been compiled. The Swift driver knows this. It goes through the file system and it figures out that there is an app that is dependent on these files. So it creates this graph internally of actions that it must take in order to get the app built. It then moves to create a list of compiler jobs that have to be done. It orders the list in the correct way so that we go from things that have jobs that have no dependencies to jobs that have the dependencies, so that the outputs of those jobs have been put in place. So you can see here that the A, B, and C files all have to be converted to object files before they can be linked into the final app. And that is the rough process of how the Swift compiler goes from your Swift code to an actual app, executable app that can be used. So again, we are more interested in what takes the most time. And what takes the most time is the compiling. So we don't really have to worry about the linking here. That's more for illustration. We're going to dive into one of these compiler jobs. Consider the first one, compile a.swift to a.o. You'll see here that when we think about these jobs, we have inputs, we have the job itself, and we have outputs. And this structure is very stable, and we're always going to be kind of coming back to the way this structure works. So inputs are a primary source file, a.swift file, other source files, b and c.swift, SDK, toolchain, there might be terminal command line flags or options, compiler options, all kinds of things go into the inputs. And the Swift driver uses the inputs to construct the actual command line invocation that it will send to the other part of the compiler, the front end. So once it has that all dialed in with all of the inputs kind of massaged into this job, it'll send that to the front end. And the front end will actually do the job of compiling Swift down to an object file. And it will produce a set of outputs, not just the object file, also some dependency information and other outputs as well. And it'll place all of that stuff into the appropriate place in your derived data folder. So this is kind of how this works. We know that the driver will construct a graph, a dependency graph, and then construct a dependency-aware list of jobs to do. And then it will pass those jobs to the front end, which will execute them in order. The front end will get outputs, it will run those jobs, it'll create inputs and put them in the appropriate place according to where they were supposed to go. So that's great. Now, the Swift driver does have some ways of speeding things up so it doesn't have to build everything all the time. That's what we're going to look at next. Knows how to limit the amount of work it has to do. We use this all the time. Let me give you an example. Let's say that I want to change something in my C file. Just the internal functionality of a method. We're not changing the interface. We're not changing how the method works. Nobody else depends on this. It just returns a list of sorted widgets, and we're changing the way it sorts. The Swift driver is still going to construct the same list of jobs that it had before. It's going to it knows that it needs A, B, and C.o, and then it needs to link those together into the app. But now, it looks at the timestamp of when I changed those files. And it says C.swift, that one was recently changed. And actually now it's newer than the last time I compiled C.o. So now it knows that it has to recompile C. So it constructs the list of jobs, but it only runs the C.swift. Great. We've saved 2/3 of the time in compiling. Fantastic, right? Let's have another one. A little bit more complicated, but similar idea. B has an enum. We're going to add a state to it. We've noticed that sometimes this fails, so we're going to add this state. A consumes this enum, but in the switch for the enum, it has a default case, so we don't really need to worry about that. We don't need to change a.swift. So in theory, maybe we don't need to compile A again. However, the Swift driver is smart enough to recognize that A does depend on B. So it's going to want to compile that again. So again, it constructs the list of job, and it says, we need to compile A, but then it looks at its dependencies that it established last time it ran the build, and said, oh, well, we are going to need to compile B again. compile A again, excuse me. So great. We already know now the Swift driver, Swift compiler, can figure out what work that it doesn't need to do when you run a build. So great, right? We're done. We don't have to worry about anything. Well, there is one problem. Let's consider one more example. Let's say you're working on your app and you get a report of a bug. And now, suddenly you decide, okay, well, I'll switch branches. And I'll fix the bug, do all the work, push up a PR, everybody's happy, everybody gets a cake, problem solved. Now I'll go back to checkout main, and I'll rebuild. Now, which compile jobs have to be rerun? The sad truth is that it's all of them. They all have to be rerun. Why is that happening? The code is the same before we checked out the bad branch and when we checked out main, so why do we have to rerun those jobs? Well, this goes back a long way. See, the Swift driver is following a pattern for determining stale source files that was established decades ago for an older paradigm, one that focused on one machine, this local machine, where there is no history. All there is your code, the last build, and that's it. So when we check out that bad branch and build it, suddenly the last build is a totally different set of code, and the Swift driver can't reconcile that. This is also going to be a problem for our CI machines. You can't just pick up derived data and plop it on another machine. It just doesn't work. So how can we help with that? This is where the compilation cache comes in. What has Apple given us then to allow us to do this? Well, we start with the compilation cache. Before we get into how that works, let's just have a look at how to turn it on. So the only documentation we really have from Apple about the compilation cache is one release note in the Xcode 26 release notes that essentially says, here's the compilation cache, here's how to turn it on. And all you have to do is you go to your build settings and you find a setting called Enable Compilation Cache and you flip it to yes. That's it. Then try running a build and then go to your derived data folder and have a look inside. What you'll see is a derived data compilation cache.noindex file. And that's where everything in the compilation cache is stored. Normally you would see a folder for every app in the compilation cache, but for every app that you've built. But with the compilation cache, you'll only see the compilation cache.noindex. Now that your build's done, go back to Xcode and have a look at the logs. You may have to build a couple of times. So look at these logs. What's going on here? We see these interesting kind of log lines. What is this? CAS. We see local cache found for key. We see CAS output. We see replay cache hit. What is this CAS and LLVM CAS? Well, to answer that, I need to take you back a bit in time to February 2022. An Apple compiler engineer added a request for comment to the LLVM message boards. LLVM is the low-level compiler infrastructure that the Swift compiler and others use to get down to the machine code that we talked about earlier. So what were they talking about when they wanted to add this CAS library? Content Addressable Storage is the acronym we're dealing with here. And essentially, content addressable storage is a way to store something inside some sort of structure, a storage system for files and for information that is addressed by its content. I'm going to go explain a little bit about how that works. So imagine that we have a file, call it hello.txt. You can do this yourself. Create a file on your computer called hello.txt and populate it with some content. Say, hello Swift Rockies. Then you're going to take the terminal and you're going to navigate to where that file is. And you're going to run this hashing function on it, this hashing tool, SHA256 sum. And what that will do is it'll take the contents of your hello.txt and it will turn that into a long string of alphanumeric characters called a hash. Now, because it works on the content, that hash will always work on that exact same content. So whatever you fill the file with, you'll always get the same hash out. So then you go ahead, you've got your hash, and you get your storage system, and you've got all these little buckets, and you put that file, the contents of that file, into that bucket. And then you address that, you reference that with the hash. So when you go back to your storage system and give it the reference hash, then you'll always get that exact same content back. So hello Swift Rockies. Oh, I spelt that wrong. Let's change that. Hello, that's better. Now it's spelled right. We're going to have to hash that again, and notice that the hash is now different because the content of the file is different. I made the change, I fixed the typo, and now the content is different and we get a totally different hash. But crucially, that hash is going to be the same no matter where I do it. You could do this on your machine and you should get the exact same hash if you have the exact same content. Now let's go and store that second version of the file in a new bucket, and we'll reference that with the new hash. Now, notice that we have two versions of the file in our storage system, one with the old hash, one with the new hash. And if I ever wanted to go back to the old content, all I would have to do was pull out the old version of the file with the old hash. Now, we've seen this before, haven't we? This looks familiar. Where have we seen this before? Oh, that's right. Git is a content addressable system. So you use this all the time already. Okay, so now we know what a CAS system is. How does our Swift build and our Swift compiler use the CAS system to save work? Now, let's go back to our earlier example with the graph and the jobs that we looked at. Remember, 3 jobs. Let's have a look at that first job, compiling a.swift to a.o and other things. So the Swift driver packages up a plan to give to the Swift front end. It has all of those inputs that we saw before, but this time, before it goes and sends that job to the front end, it takes all of the contents of the a.swift file and any other files and any other inputs it needs, and it puts them all together and it hashes all of those all together. So you get this really stable identifier that identifies that one compilation uniquely. Nothing else that can ever get that hash. So once it has that output key, then it passes that to the Swift front end, and it says you need to compile this. Now, the Swift driver might not pass that to the Swift front end because, as we saw before, sometimes the Swift driver says, "Hey, I can do incremental builds here. I don't need to do this work." So it's still doing incremental builds, but if it decides that a file does need to be compiled, then it passes that to the front end. And then we proceed with what happens. Now the front end might do the same work that it did before, but first it's going to take that same key that was passed by the driver as an input key. Once it has the input key, it's going to check the LLVM cache that it has access to, which is the one you find in derived data. If there's a cache miss, if it doesn't find the output files inside the cache, then it's going to say, okay, I need to do the compile. It's going to do that same compile we saw earlier, and it's going to take all those outputs and it's going to store them into the cache, into the content addressable storage. Then it's going to report back, and we'll have that output key as a record of what was built before. But the real magic, the real speed up comes if there's a cache hit. If we've ever built that exact version of a.swift before, if those exact inputs, then we'll get a cache hit. And the Swift front end will simply be able to replay all of those outputs from the cache and put them where they need to go. And that's where the real speed up is. So the good news is, this just works. You turn it on and it will just start making your builds faster. Clean builds can be much faster. This is my small project. I do clean builds on an M1 Pro, and without the cache turned on, a clean build takes about 15 seconds. It's not a huge project. With the cache turned on and primed, a clean build takes about 8.2 seconds. So that is from, I could I could delete the folder, clone fresh, and I'll get almost a 50% speed up in my build times. So that's great for local. You're kind of wondering now, okay, what about CI? What about helping my friends, helping my colleagues? So the remote cache is also possible. So you can see here, on a local machine, we have Xcode communicating with the derived data cache. Now, the trouble is, it's a bit more complicated to get a remote cache. Essentially, Xcode comes with a plugin that has a gRPC client inside it. That gRPC client, if you turn on the remote cache, will try to communicate with a socket, with a gRPC socket located on the same machine. Just a file that's a gRPC socket on the same machine. That socket needs to send all of the information, all the requests and responses to the remote cache sitting on another machine somewhere. And if every developer's computer is communicating via the plugin rather than towards the derived data cache, then that's what you'll get. It'll go to the plugin and it'll go to the remote server and it'll bring the outputs from the remote cache. Now, how do we get that to work? There are a couple of more build settings that you have to enable. I'm sorry for the wall of text here. We'll have a look at how to enable those build settings. Unfortunately, Xcode doesn't give us any UI for this. Xcode doesn't really tell you that these build settings exist. You have to add these build settings as user-defined settings in your settings. And also, it gets even a little bit trickier because what you see here is what is provided by Xcode. Everything else in the picture is something you have to bring yourself. You actually have to have a gRPC socket that will proxy the CAS plugin client requests to a remote machine, and you actually have to bring the remote machine and the remote cache as well. So that's a lot of work, and Xcode and Apple have not provided us anything there yet. With that said, someone has. So my recommendation is to use Twist. Now, Marek is here at Swift Rockies. He's speaking on day 2, and I'm sure he would be happy to talk to you about the Twist remote cache. It does all of that for us. The Twist remote cache will proxy all of that information, and you can it's very easy to use. So right now, that's probably my recommendation to get remote compilation cache working. They've also provided, in a wonderful blog post that I highly recommend you read, some performance data. Now it's interesting to look at this performance data because you can see that depending on which app it is, you might get a lot of speed up and maybe not so much. We should probably ask, what's going on here? Why is that? Well, there are some limitations about Xcode's compilation cache that we need to be aware of. What's not cached? The big one is Swift packages. Swift packages are not part of the compilation cache. Having said that, there is currently a pitch on the Swift forums to enable this support. So we should watch that space because that may be something that we can get to at some point in the future. Non-code resources, so images, movie files, nibs, linking, that sort of thing, data models, these don't get cached either. So if you have a lot of video in your app, that might take longer. Release builds. There's no caching on release builds due to the way that the Swift compiler is optimized. None of the hashes would make sense when that happens. So the inputs would not match the outputs, the caches wouldn't. So you don't get any release build caching. Also, if you already know a little bit about caching, you'll know that the Twist cache and also Bazel usually operate on the module level. So they might cache each one of your sub-projects as a module, and then bring that whole binary back out of the cache. But that's not how compilation cache works. Compilation cache works on the level of a Swift compiler job. So one file at a time. So you could get thousands of cache hits in a single build with compilation cache very easily. So those are things to be aware of when you're thinking about how to structure your code. So unfortunately, if you have all of your code in Swift packages right now, it's likely not going to make a huge difference for you. You would have to decompose that code and put it into maybe sub projects in your code. And I'm not sure whether the trade-off is worth it just yet, especially if Swift packages do become supported in the future. So what have we talked about in this talk? Well, we talked about how long how long we spend compiling, and how we're always trying to reduce that. We talked about the current state of things. We talked about the Swift compiler, how the driver creates a graph and then translates that into a list of jobs that get built, that get run on the Swift front end. We talked about how it uses incremental builds to try and reduce that work, but that incremental builds can be really difficult to use because they're built for an older paradigm. We talked about Xcode's compilation cache. We talked about how to turn it on, and we talked about how it takes the jobs that the driver asks the Swift front end to compile and replays them from the LLVM cache. We also talked about some of the limitations of the compilation cache. Also that right now, the remote cache is something that we have to bring ourselves, but we talked also about how some of the community have given that to us. So I want to thank you for attending my talk, and if you're curious about the background in this talk, it's actually a painting by the talented Robin Olsen, and you can find her on Instagram at robin.olsen. And this is a painting of the Three Sisters in Calgary, Alberta, which if you're going to the Rockies after the conference, you might actually find. Thank you very much. Hi again. I thought I'd provide a little bonus content to my talk since a lot of people have been asking me about Bazel and how that fits in. So I did actually have a bunch of slides on Bazel that I had to cut because I didn't have time. But in this format, I think we can get into it. So the difference between Bazel and Xcode Cloud is that Bazel actually replaces, or the difference between Bazel and compilation cache is that Bazel actually replaces everything. When you define a Bazel project, you create this build.bazel file, and it sits in the root of your repo. And you actually have to define an Xcode project within that Bazel file. So you'll notice here, we're defining an Xcode project name, top level targets. You actually define the targets in here. The whole idea is that you define an Xcode project, an iOS application, maybe some Swift libraries, and you define all of the details that you're going to need. Now, there are a couple of projects that give you some predefined rules that you can customize. But I think the thing that it's worth being aware of is that when you use Bazel, you are actually replacing everything that Xcode, that Apple provides. You're replacing your Xcode project. So these are basically functions provided to you by the iOS rules project, which is a sub-project of Bazel, which provides specific support for iOS within the Bazel ecosystem. And so the Xcode proj then contains an iOS application, which then might contain Swift libraries. And all of these things, you'll notice we're specifying bundle ID, source files, module names, dependencies, info plist, and all that kind of thing. And the whole point of that is that these are supposed to be pure functions, and they're supposed to specify absolutely everything that can be specified within in order to create these things. So the Xcode proj function is actually going to create an Xcode project. The iOS application is actually going to create an iOS app within the project, and Swift library is going to create frameworks within that. And it's going to do it the way that Bazel expects to do it. It will eventually be able to be built the same way that an Xcode project will, but generally speaking, you don't work within Xcode when you're using Bazel. You work within whatever your favorite text editor is. A lot of people end up using VS Code because it has good support for Bazel. So what happens is that all of these actions, or all of these things, so Bazel basically converts all these functions to actions. So they analyze this app, generate an Xcode project metadata, assemble the .app, compile Swift sources, all of this stuff. All these actions, these are sort of like the Swift driver's actions when it creates, but they're at a level that's higher up than what the Swift driver is doing. Swift driver is more concerned with just the compilation phase, but Bazel is actually generating a graph of actions that include all of the phases we looked at. So the processing, compiling, linking, bundling, and then even signing, right? So Bazel's generating those same kind of graph and actions for all of those phases, absolutely everything that it takes to build a project. So so similarly to the way that compilation cache works, Bazel is going to convert all of those actions to hashes. So as long as those actions don't change, Bazel can actually cache everything, not simply the results of the compilations, but it can cache whole modules. It can cache Xcode projects. It can cache results. It can cache out all the outputs, absolutely everything. And that's kind of, I think, one of the things that teams get when they switch to Bazel is they get a system that just simply looks at building projects in a totally different way from Xcode. So, and with that comes a lot of advantages for sure, but it also comes, you really are separating yourself from the Apple ecosystem there.